In this video, I will explain what light is and how it travels. I will also explain what relative distance is and how the fundamental nature of light deals with it. All of my explanations are based on the three fundamental forms of energy. Just a quick reminder. The energy ocean fills the immensity of space. All particles are tiny tornadoes of energy, and our velocity through the energy ocean keeps all of our atoms spinning. We walk into a room, flip a switch, and a light turns on. It is such a common occurrence that most of us don't give it a second thought. But how light gets from the light bulb to the four walls of the room is a mystery that has baffled scientists for hundreds of years. Light is entirely a particle phenomenon, but the particles, photons, do some unexpected things in the process of delivering their light. What is an electron? When a light is turned off, an atom of the tungsten filament is at the ground state, small. Because of its velocity through the energy ocean, it vibrates like a flag waving in a stiff breeze. Because of this vibration, it periodically snaps off part of its tail, which is an electron, also small. What is a photon? When the light is turned on, an atom of tungsten is elevated above the ground state and becomes larger. It vibrates more vigorously and emits a larger part of its tail, which is a photon, also larger. Surface atoms of the tungsten element are most energized. Atoms deeper towards the center of the wire are accordingly less energized. These variously energized atoms account for the variously energized photons. Every light source emits a wide variety of photon sizes traveling at various speeds. Consider a yellow laser whose beam is reasonably well focused. We will track some of its photons on a journey of 100 feet. First, I call your attention to the compact arrangement of the photons as they initially leave the laser. Next, we take a snapshot of the photons at 50 feet. Here we can see that the photons have lost energy, mass and speed, as they push their way through the energy ocean. In addition, we can see that they are more spread out. And at 100 feet, we can see even more energy loss and more dispersion. At 100 feet, this batch of photons have lost enough energy to be detected, but additional photons with initial mass and velocity much greater than these have been pushing their way through the other photons so they can be detected at 200 feet. Now, these faster, more energetic photons cause the spreading of the slower photons. No matter how tightly focused is a beam of light, the normal process of delivering that light to distant locations will cause that beam to spread. Those faster photons are not the only influence that causes the spreading of light. The process of losing photon energy in quantum leaps sends smaller photon remnants flying off in somewhat random directions. They may be redirected along the general flow of the other photons, but most of the photons involved in delivering the light are never seen. Some lost so much energy that they may never arrive at the detector. And by the time some photons reach the detector, they've lost too much energy to be detected. Others were too energetic and passed right through the detector. If the detector were closer to the laser, it would have detected photons that were initially less energetic. Conversely, at a greater distance, it would have detected photons that were initially more energetic. Wherever the detector is placed, it would have detected only those photons which had lost sufficient energy to fall into its appropriate energy range. A source has no way of knowing how far its light has to travel, so it broadcasts a wide range of photons to accommodate all possible viewers. Several brief definitions are in order. First, I define physical distance as that which can be measured by a yardstick or similar device. Relative distance is the actual distance traveled between 2 points when system motion is involved. Now, the difference between these two distances only becomes meaningful when the system motion is significant with respect to the speed of light. It is within the fundamental nature of light to compensate for variations in relative distance due to motion. I will explain how the true nature of light accomplishes this. In discussions about relativity, scientists often assume that two things are true about the fundamentals. The first assumption is that all light travels at a constant speed c. And secondly, it is assumed that all the laws of science remain the same regardless of the speed of the observer. One of those assumptions is true, and the other is not. The following thought experiment demonstrates the problem with the assumption about light. Consider a spaceship sitting on the runway, ready for takeoff. It contains an experiment that deals with the nature of light. Near the front of the ship is a lamp that emits a single pulse of red light when activated. Near the rear of the ship, 50 feet away, is a yellow lamp. There is a color blending lens located between them, 25 feet from each lamp. The test is performed before takeoff, and each lamp is activated at the same time, and light proceeds to the blending lens. Because light travels at the same speed and it must travel 25 feet from both lamps, the lights both arrive at the blending lens at the same time. The red and yellow colors blend to produce an orange color. The same experiment is performed after the spaceship takes off and attains a speed that is 40% of c, the speed of light. At that speed, the relative travel distance of the yellow light increases to 35 feet. The physical position of the lens has not changed. It is still 25 feet from each lamp, but the blending lens moved an additional 10 feet forward, away from the original position of the yellow lamp before the light arrived, causing it to travel an additional 10 feet. At the same time, the lens moved 10 feet closer to the original location of the red lamp, shortening the travel distance of the red light to 15 feet. Now, if light really travels at a constant speed c, then the light from both lamps must be traveling at the same speed, and since the red light has the shorter distance to travel, it arrives at the lens first. The yellow light had to travel further and arrives later. Because the lights arrived at different times, the colors do not blend, so no orange color appears. Now, if colors blend to produce orange when the spaceship is parked on the runway, but do not blend to produce orange when traveling at 40% of c, then it would appear that this particular law of science does not remain the same for all speeds. In my opinion, scientists have oversimplified the true nature of light. The assumption that all light travels at a constant speed c is incorrect. While it is correct that the speed of light in a vacuum will always measure at c, it is incorrect to assume that all the photons produced by a given light source are all the same size and traveling at the same speed. Gunter Nimms performed an experiment transmitting recorded music on a microwave. He split the signal, sending half through the air and half through a 14-centimeter barrier. He measured the arrival times of both signals on an oscilloscope. The signal traveling through the air measured at speed c. However, the signal through the barrier measured at 4.7 times c. In my opinion, the Gunter Nimms experiment clearly demonstrates that a given light source, microwaves in this case, emits photons at a wide range of speeds. Now let's see what light does with all those photons. Every light source emits photons at a wide range of sizes and speeds. They are represented on this arbitrary photon energy scale from 1 to 16. Photons lose energy as they move through the energy ocean. More energetic photons travel further than less energetic photons. Now, these photons literally rain down on our various detectors, but the atoms of any detector will only absorb photons in a very narrow energy range, in this case between 1 and 2. If photons lose enough energy to fall below the detector's range before they reach the detector, then those photons will not be detected. And if the photons are too energetic when they reach the detector, they will pass right through and not be detected. The detector will only absorb those photons which had lost sufficient energy on their journey to fall into the energy range of the blending lens. Photons of yellow light that began at energy level 13 traveled faster than the photons of red light that began at level 7. They both arrived at the blending lens at the same time and produced an orange color. All other photons continued on their journey, losing energy as they traveled, contributing the remaining essence to the energy ocean. It is in the very nature of light to compensate for variations in relative distance due to motion. The various speeds of the photons make it appear that the speed of light remains constant regardless of the speed of the observer. This chart shows the effect of a barrier like the one Gunter Nimps used on his microwave beam. A photon at initial energy 8 would normally be detected somewhere between points B and C, but traveling through a barrier caused the photons to lose enough energy to be detected much earlier than normal, just a little past point A. Because they were much more energetic than the photons that would normally be detected at that distance, they arrived much sooner than expected. In my opinion, that is why the Gunter Nimps experiment demonstrated light traveling through a barrier at 4.7 times the normal speed of light. A well-designed experiment cannot possibly produce such variations in light speed unless those variations are a fundamental part of the very light you are studying. You will never understand the true nature of light if you only study the photons that are absorbed into your detector. The unseen photons that deliver that light are equally important. There is more to light than meets the eye. This chart shows how actual photon energy loss appears, superimposed on the typical loss chart. Photon energies from a lamp are shown on the left axis, and the vertical maroon rectangle represents the photodetector. Photon energy is represented by the reverse voltage required to bring the photocurrent down to zero. I used a matrix of 15 mini incandescent lamps to maintain a constant photocurrent of 21,300 picoamps for each reading. The readings only reflected the most energetic photons at each distance. As the detector was moved further away, I turned on another lamp and adjusted the distance until the photocurrent read 21,300. That is why the distance increments are not uniform. All of the photons were constantly flooding the detector, but only those photons that had lost enough energy at the selected distance were detected. As the detector moved to the right, successively more energetic photons were detected, and the more energetic photons were not detected at the shorter distances, even though they were obviously present. They only appeared as the distance was increased. To an observer on the spaceship, the speed of light for both colors is still measured at c. To him, both lights traveled 25 feet and arrived at the same time. But the actual speed of the photons varied significantly to compensate for the variations in relative distance. The detector, the blending lens, ignored all of the other photons, absorbing only those that fell into its energy range. Those photons arrived at exactly the same time, producing an orange color. The variations in relative distance, while very real, went unnoticed and were of no concern to the onboard observer. The fundamental nature of light just took care of it. When you understand light this way, all the laws of science remain the same. In this case, we have blended red and yellow light producing an orange color. It was orange at 40% of C as well as before takeoff, and the speed of each light measured at C in both cases, but it took the variable speed of photons to make it happen. This understanding of light also explains the mystery of the Michelson-Morley experiment. In the late 1800s, scientists were debating theories about how light traveled through space. Some thought there must be a substance, they called it ether, that fills space so light would have a medium to travel through, like sound waves traveling through air. Well, Michelson and Morley designed an experiment assuming that if light traveled through ether, its speed would be affected. So they measured the speed of light coming from a distant star while the Earth, in its orbit around the Sun, was moving towards that star, and again while the Earth was moving away from it. They expected to find a 37 mile per second difference in speed, but the speed of light measured the same in both cases. And this is one of the unexplained dilemmas about light. Even if a light source is moving towards you at half the speed of light, it will still measure only as c, the normal speed of light, instead of the expected 1.5 times c. And while scientists know that this is true, there is no currently accepted theory of light that can explain how this is possible. This chart, showing photon energy loss over distance, indicates why Michelson and Morley were not able to detect any difference in light speed. The center of the chart shows a range of photon energies, from 1 to 9, emitted from the distant star. The left side of the chart shows a reduction in the relative travel distance of the light because they were moving towards the star. It was similar to the shorter distance of the red light to the blending lens in the earlier spaceship example. Photons emitted at energy level 5 were adequate to arrive at the detector at the proper energy range. The right side of the chart shows an increase in relative travel distance of the light because we were moving away from the star. And this is similar to what happened to the spaceship's yellow light. Photons emitted at energy level 8 were required to travel a little further in order to be absorbed into the atoms of the detector. But in both cases, the light arriving at the detector measured at speed c, but the photons delivering the light were traveling at different speeds to compensate for the variations in relative distance due to the motion of the Earth. Because the fundamental nature of light compensates for variations in relative distance due to motion, it was never possible to measure the speed of light as anything other than c. Consequently, their attempts to look for variations in light speed to determine if something like ether actually filled the immensity of space were doomed to failure from the very beginning. Space is filled with energy, and it affects the speed of everything traveling through it, including atoms and photons. It just works differently from their expectations of ether. Scientists have long been baffled by results from the traditional two-slit light tests. Most of the confusion stems from the assumption that the photons that registered the fringes on the target plate were the only photons passing through the slits. As I explained earlier in this video, light uses many photons at varying speeds and energy levels to take light from a source to some target detector. While they only become visible when they lose enough energy to fall into the range of the detector, there are always plenty of other photons not quite ready for detection still pushing their way through the two slits. Even when they thought they were only letting one photon at a time through the slits, it was only one visible photon at a time, but they never travel alone.